Hello everyone. So in this video, I'd like to talk about how we can use cylindrical shells in several other contexts in addition to the model case that we had before. And to do that, I think it's important to keep in mind, or useful to keep in mind, the key idea, which is that we're integrating volumes of shells, and we get the shells from integrating typical rectangles. And to find the volume of the shell, we have to do the circumference times the height times the thickness. So let's see how that works in several examples. So let's start off by looking at the region between curves. So before we looked at the region bounded by the axis in a curve, let's look at the region between two curves. So find the volume generated by rotating about the y-axis. The region bounded by y equals x squared and y equals 6x minus 2x squared. Okay, so let's first think about what that region looks like. We're not specified any x values, so this region is going to start and end when the curves intersect. So here is the picture, right? We have, ignoring the rectangle for a second, we have y equals 6x minus x 2x squared as the top curve, y equals x squared as the bottom curve going up, and the region is everything between them. Okay, and now we're supposed to find the volume when we revolve this around the y-axis. So to do that, we want to find what a typical shell looks like. And a typical shell comes from a typical rectangle. So we said the idea was to pick a point x on the x-axis, and then we draw the rectangle around x, which has thickness dx. And before, when we were looking at just the area bounded by one curve, we drew the rectangle between the curve and the axis. Now we're looking at the area between two curves. So we're going to look at the rectangle, which is bounded by the two curves. So we have one curve on top, one curve below. The rectangle runs between the two curves, right? It's approximating the region. The bottom curve is x squared. The top curve is 6x minus 2x squared. The height of the rectangle then is going to be the top curve minus the bottom curve, right? It's the difference in the y values, right? This is the difference in the y values. So we have to do 6x minus 2x squared minus x squared. So this is going to be the height of our rectangle. The thickness of the rectangle is dx. And then the distance from the rectangle to the axis where we're revolving around is x. And then if we think what happens to this rectangle as we revolve around the y-axis, right, this rectangle becomes a typical shell. It becomes a cylindrical shell. The radius of the shell, or the average radius of the shell, is x. The thickness of the shell is dx. The height of the shell is 6x minus 2x squared minus x squared. So this is everything we need now to conclude, right? So in a typical shell, the radius was x, so the circumference is 2 pi x. The height is the difference in the y values, right? It was the height of the original rectangle. So that's going to be 6x minus 3x squared. And the thickness is dx. And we said that to find the volume of a shell, we have to multiply the circumference times the height times the thickness. And then to find the volume of the region, we have to integrate that. So here is the volume of the shell, 2 pi x, 6x minus, if we simplify 6x minus 3x squared, times the thickness, which is dx. And then we integrate to get the full volume. Where do we get shells, or where do we get rectangles? Well, it starts when x equals 0, and then it ends when x equals 2. So we're going to integrate from 0 to 2. Okay, and then we could pull out the 2 pi. We could multiply the x through, so we get 6x squared minus 3x cubed. We apply fundamental theorem of calculus, plug in the endpoints, subtract, simplify everything. You will get 8 pi in the end. So here, the only main difference was, or the only real difference was, the height of the rectangle was different. The height of the rectangle was the difference in the y values. Okay, so let's see some more variants. So when did we use cylindrical shells? So we just used cylindrical shells to find volumes of revolution about the y-axis by working in terms of x. So there, the key point was that we couldn't use slices, or we chose not to use slices because we didn't want to write x in terms of y. Either because that's what we were asked to do in the question, or maybe there are lots of functions where we cannot invert to find x in terms of y. So as we did before with slicing, we can swap everywhere the x and y to get another rule for integrating or working in terms of y. So we can also use shells to find volumes of revolution about the x-axis. So rather than the y-axis, we switch to the x-axis by working in terms of y. So we get another rule for rotating about the x-axis, working in terms of y. So now it seems like we have a lot of different methods. Sometimes we'll be specified what method to use, but if we're just given free rein, how do we decide what method? It seems kind of complicated, but luckily there is a table to restore our sanity. So let's remember what is going on. So suppose we're working in terms of x and we rotate about the x-axis. In that case, the cross-sections are going to be disks or washers. Those are the problems we started with in 6.2. So then we're going to want to use cross-sections, right? The cross-sections are disks or annuli. We find the area, we integrate it, that's cross-sections. But if we want to work in terms of x and rotate about the y-axis, that's what we started doing with cylindrical shells, then we're going to use shells because we cannot work out x in terms of y in order to use slices. And then if we swap x and y around, we see the opposite rules, right? Working in terms of y, for instance, if we swap the rule for rotate about x, work in terms of x, then rotate about y, working in terms of y, will be essentially the same. We're going to use cross sections. Or if we swap the rule for working in terms of x and rotating about y, if we swap everywhere the x and y, we get the corresponding rule. If we're working in terms of y and we're rotating about the x-axis, then we should use shells. So I think it's helpful to keep in mind this table. It will be really useful to help you decide what to use. Or even if you just remember the top line, right? If we're working in terms of x and we're going about the x-axis, if you have a choice, then use cross sections. And if you're working in terms of x and you rotate about the y-axis, use shells. And if you're working in terms of y, you have to swap everywhere the x and y and decide what rule to take. So sometimes you'll be told what method to use, but sometimes it's useful to think about this table. Okay, so let's do an example where we are doing shells with x in terms of y. So let's see how that works. And here we're going to revisit an example we saw before. So we're going to find the volume when we rotate the region under the curve y equals square root x above the x-axis from x equals 0 to x equals 1. And we did this before with cross sections, and I think that's by far the easiest method. But let's see how it works with shells. So this one we can invert, right? If y is square root of x, we can write x equals y squared. So this one we could use either method. So let's try to use shells. So since we're rotating about the x-axis and we're using shells, our shells are supposed to be in terms of y, right? If we rotate about the y-axis and use shells, our shells are supposed to be in terms of x. So now instead we're about the x-axis, we're using shells, our shells are supposed to be in terms of y. So here is the region under y equals square root x, or equivalently x equals y squared, above the x-axis from 0 to 1. So here is our region. We're supposed to use shells in terms of y, so we fix a point y on the y-axis, and then we are supposed to draw a little rectangle with thickness delta dx, or width dx, sorry, with width dy. So here at y is our little rectangle with thickness dy. And then the height of the rectangle is going to be 1 minus y squared, and the distance of the rectangle to the axis where we're revolving around is going to be y, because we're rotating about around the x-axis. So we know all the dimensions for our rectangle. Let's think about the shell, right? If we rotate this rectangle around the x-axis, we get another kind of shell. We know the circumference, we know the height, we know the thickness. So the typical shell is going to be 2 pi y, because we do 2 pi times the radius. The radius is the distance of the shell to the axis, that's y. The height of the shell is 1 minus y squared, and then the thickness of the shell is dy. So we can find the typical shell volume. Okay, and now we find the typical shell volume. We do the same thing, right? Y runs from y equals 0 up to y equals 1. We integrate it, we get the volume. If you pull out the 2 pi, multiply through by the y, use fundamental theorem of calculus, you can get pi over 2. Okay, so let's see one more example. So we know how to now cover, rotating about the x-axis or rotating about the y-axis using either sections or shells. Let's see how to use shells if we rotate around a different line. So let's find the volume of the solid that we obtain if we rotate the region bounded by y equals x minus x squared and y equals 0, about not an axis, not the x or y axis, but now about the line x equals 2. So the only thing that's really going to change is going to be the shell radius, right? So here is our shape, right? We have y equals x minus x squared. It runs from x equals 0 to x equals 1. That's where it intersects the x-axis, y equals 0. And now we have to think, the line x equals 2, is it more like the x-axis or more like the y-axis? Okay, x equals 2 is a vertical line, and the y-axis is a vertical line. So this is going to be more like when we were revolving around the y-axis. So if we remember what we did when we revolved around the y-axis, we fixed the point x, and we made a small rectangle around x. Then we figured out the volume of the shell in terms of x, and we integrate that volume. So we have to do the same thing. So we're going to have a rectangle centered at x with small thickness dx. So this is going to be a rectangle that has thickness dx. The height is x minus x squared. And now the radius has changed because the radius is the distance to the line where we're revolving, right? You can imagine the rectangle moves around the axis where we're revolving. The radius is going to be the distance of our rectangle to the place where we're revolving. So that's going to be, so here the rectangle is at x, we're revolving at 2. That distance between those is 2 minus x. So now the radius is 2 minus x. So in general, if you're revolving around a line which is parallel to one of the axes, think, what is this more like? Is it more like the x-axis or is it more like the y-axis? Meaning, which one is it parallel to? Here we had x equals 2, it's more like the y-axis. So we're going to follow the method for the y-axis, but we had to change the radius. Okay, so that's our strategy. So now we can write down the typical shell volume, right? We know the radius is 2 minus x. The circumference is 2 pi times the radius, so 2 pi times 2 minus x. The height is x minus x squared. The thickness is dx, so this is our typical shell volume. And then we just have to integrate the volume of the typical shell. So the shells start when x equals 0 up to when x equals 1. So we have to integrate this from 0 to 1 Okay, we would pull out the 2 pi, multiply out everything in terms of x, use fundamental theorem of calculus, find the antiderivative, plug in the endpoint, subtract. It would be a bit of a calculation, but in the end, you'll get pi over 2. Okay, so with this video, the key takeaway is that in the model example with shells, we had y in terms of x, we revolved around the y-axis. We can also work with x in terms of y and use shells to revolve around the x-axis. So in general, it can be a little bit complicated, but remember the table, right? That's going to help us to decide whether we should use slices or shells. So sometimes you'll be told which to use, but otherwise try to use the simplest method. And then we can also revolve around lines that are not parallel to the axes. In that case, we should keep in mind that the radius is going to change. And to get started, we should think, are we more like the x-axis, meaning are we parallel to the x-axis? Are we more like the y-axis, like in this example, meaning we're parallel to the y-axis? Okay, thanks everyone. See you next time.